All right, as Krista said, unlike some organizations, Berkeley runs on time. So as you'll see in the preview session, so the model is those of you on deck, the current speaker will be there. You see Chris Celio's next, and Martin Moss. You'll see your name rolls up. There's about 20 people. We'll keep everybody to 3 minutes. I'll keep track of the time. And you're trying to do an advertisement to get the people to come by your poster. The way this is going to work is after this, we go to dinner. And are you going to do the breakout topics? Okay, after the poster preview. So don't get up and leave. We'll tell you about how dinner is organized, and we'll do dinner, and then we'll do the poster. So you're trying to get people to come by and talk to you the poster. First person is Dick Seitz, who I've a long-term friend, the architect of the Alpha instruction set architecture, and at Google's for several years. Here you go.
Hi, I'm Dick. So I'm not going to take 3 minutes. I have a poster on Datacenter Extension. I just came to encourage a lot of students to think about not just cell phones and spec marks, but to think about the other side of the cell phones, and that's the data centers of the world with thousands of servers that spend a huge amount of time moving data. They spend running thousands of threads that interact sometimes very badly on very short time scales. It's an environment where delaying 5 microseconds to deliver an interrupt can make a difference. Spinning up an idle CPU core from low power for 75 microseconds is huge. So there's a lot of that. We have a serious issue across the industry with cache isolation if we're running unrelated programs on shared processors. And one of them is moving huge amounts of data. You can fill up all the second and third level caches and just hose the other programs, and there's no way to see it. So we also need much better visibility measurement. In particular, I think for data centers, you need to switch your viewpoint from CPU time to wall clock time. You know, we have to deliver something back to a user in 200 milliseconds. We need to understand where all the wall clock time went. A lot of it goes into not executing. It goes into waiting for something, except there's very bad visibility about what we're waiting for. Once you know what you're waiting for, it's pretty easy to fix. Timers, network, CPU, getting scheduled on the CPU, disk, and locks, software locks. And we need more visibility on all of these things. Thank you.
Hi, my name is Chris Celio. I'm a graduate student here at UC Berkeley, advised by Krista Sanovich and Dave Patterson. For the first poster, I'm going to put on my education hat and talk about the Sodor processor collection that is freely available. And this is built to help teach undergrad computer architecture, also kind of serve as an introduction to Chisel and an introduction to RISC-V. And kind of one of the main goals was actually to provide a whole set of cores that actually matched the lecture slides, and the variable names matched the lecture slides, so that way students could actually physically play with what they saw in the classroom. Unfortunately, that means that there's not really a focus on making these synthesizable. But we do provide a whole menagerie of these 32-bit integer cores, a 1-stage, 2-stage, 5-stage. And you can parameterize, so like the 5-stage you can turn on and off bypassing. There's a 3-stage which demonstrates how to talk to synchronous scratch pads. And there's also really cool a micro-coded bus-based design. So in Chisel, we actually describe microcode, and then we actually have a compiler in Chisel that takes the microcode, figures out the addresses, links it together, generates a ROM, and so you have a very small data path that's shown on this slide. And we actually force our students to write microcode in the class as part of our tests. So anyways, if you want to see these, they are available at GitHub at RISC-V Sodor or at riscv.org or at Chisel. And come talk to my poster if you want to talk about education, Chisel, RISC-V, or architecture. So I'm now going to move over, take off my education hat, talk about research. For my thesis, I've been building the Berkeley out-of-order machine. Our goal here is to kind of create a realistic baseline strawman RISC-V out-of-order processor because we really want to explore power, area, energy efficiency designs. A lot of computer architecture research focuses on software simulators. They can be really good for prototyping, but it's hard to be confident they're really grounded in reality. Or that you've captured all the inputs to the system. And if you really want to, you can't really push that through the tool flow if you want area or energy. And while there's things like McPat, they're not really balanced to, they're tuned to real hardware, and we're interested in building something maybe newer, exotic, or different. So we can't really, we're not quite confident about that. And then why Chisel? It's a more productive language for us, and it's very easy for us to describe parameterized hardware. To show a little bit about the processor, this is kind of our baseline strawman design. It implements our RISC-V ISA. Right now I'm hardening the integer part of the ISA, so no floating point yet. It is superscalar, parameterized, it has full branch speculation, load store queue with loads going fully out of order with respect to stores and loads. It's a short pipeline. I've not really pushed this too hard, but I did verify I could go at least over 2.2 gigahertz. Apologies, it's not 5 gigahertz. I'm only one person, and I don't have a team of SRAM designers or people that can fool the tools. Right now our limit is the SRAM that we're given. It's only 8,000 lines of Chisel code, and this does fit into the rocket ship stack that we were talking about in the previous lecture. So I actually get to reuse a lot of significant components that I kind of get for free. I get 2 posters, so I get twice the time.
Okay.
I got 1 more minute. The current status, we have used this actually in our own undergrad class for 3 times now. We can give them the code. They can play around with branch predictors, load store units, issue windows, and see how they can change performance. This does run on our ZBoard FPGA at over 50 megahertz. And I have been executing Drystone, CoreMark, and some of the spec input tests, which is about 10 to 100 billion cycles. Right now, I'm still trying to bring up the performance a bit better. Unfortunately, adding more features means adding more bugs. And while I'm pretty good at getting it going a couple billion cycles, I need to kind of develop the story for getting it at 1 trillion cycles. And then I can explore trade-offs and hopefully get a paper out of this and then open source it for you all. Anyways, come talk to my poster if you want to talk about Chisel, RISC-V, processors, and all that fun stuff. Thanks.
So the next 2 poster previews kind of belong together. Andrew already talked a little bit about Pokey, but we have a poster as well that gives a little bit more details. So if you want to compile a RISC-V application today, you have to go through a lot of steps. You first have to download and compile the RISC-V toolchain with GCC, bin utils, etc. Then you have to build Linux. Then you have to figure out all the dependencies, cross-compile all of them, which means you download them, you patch them, then you have to compile them, and you have to install them into the right locations of your sysroot. And then eventually you have to package up all these things to an image and run it on QEMU or real hardware. So this approach is quite a lot of work, and it's also quite error-prone, so it's easy to get a step wrong in the middle and then have to start all over again. It's also hard to reproduce for other people, so all the work that you did bringing up an application, other people are probably going to have to do it again. And finally, it's very hard to react to changing dependencies. For example, if there was a patch to the toolchain, you potentially have to recompile a lot of things. So in order to make all these things easier, we ported the Yocto project, which is a Linux distribution generator. So it is a system that can automate all these steps above. It can download all the different things you need, including your toolchain, QEMU, and Linux. It applies any patches that it needs. It installs them into your image and wraps it up in such a way that you can use it easily. It consists of 2 parts. The first part is a repository of hundreds of recipes that tell it how to compile a lot of different packages for different platforms. And the second part is a highly parallel build tool that takes these recipes and basically just executes all the different steps, downloading applications, patching them, cross-compiling them, and then produces packages that you can use with a package manager. It produces images, and you can also generate binary SDKs that you can directly ship to customers. And the nice thing this does for us, it gives us hundreds of packages that just build out of the box, so we get a whole lot more software we can run on RISC-V, including things like Python.
There we go. I'm Palmer. I'm working on the other half of our Linux distribution story. So while Martin ported Pokey, which is an embedded distro, I'm working on Gen 2, which is the sort of distribution you would run on, say, a desktop or a laptop. It's actually what I run on my laptop. So I'm in the middle of doing a port of this to RISC-V. And I've got a demo up and running. You can run a web browser and go to Twitter on an emulated RISC-V QEMU machine, which is kind of neat. It's like having a real computer. So you should come by and see the demo. So Gen 2 itself is kind of interesting because it's the basis for a number of somewhat popular Linux distributions. It's actually the basis for Open Embedded. They're based on the same package building toolchain. And it's also the basis for Google's Chrome OS operating system. So while Gen 2 itself isn't that widely used, a lot of derivatives of it are. So you can come by and you can see some stuff running.
I'm Craig Steele, Totline LLC. And, I wonder if you've ever found yourself in the following situation. You build some cool piece of new hardware with a really nifty innovation that is going to make the world a lot better. And you try to interest potential users, and they say, there's no software. It's impossible to program. We'll use something easier like an FPGA. That's the end of the conversation. So I have had that conversation. And the particularly when you're interested in building something with a lot of cores, the speed of emulation is something that's very important for software, the quality of life for software developers. And I'm very encouraged here that the RISC project goal of enabling, that one of the major goals is not building open hardware, but massive common denominator software that can run on any of the systems. So that software is really important. So the state of the art for functional simulation of ISAs is QEMU. It has some problems that, particularly in the difficulty of making a multi-threaded version that can run on multi-core. The code base is not to everyone's taste. And our approach is to use a different language, not to actually generate the, have a tiny code generator that does dynamic binary translation explicitly, but to code in a higher level language, which happens to be Lua, and let a JIT compiler optimize that translated code. And Lua JIT is a great compiler. It gets about 50 or 60% of native C in many applications. So we get performance comparable. Anything is comparable. You can say, well, it's 1,000 to 1. But we're in the ballpark. We're, it's so immature, it's unfair to say anything, but we're between Spike and QEMU. And have a multi-threaded implementation, so there's a lot of upside available there. And can load Lua modules and link to, with an excellent FFI interface, to external C libraries if you have fixed function modules that you'd like to get that extra performance out of, rather than something that's general purpose programmable. So drop by. Yes,
so basically during my talk I had a picture of the setup that we have, something a RISC-V implementation running on an FPGA with these GDB connections, host IO connections, and so on. We'll try doing that in a demo here. We have the setup running under VNC back in Massachusetts, and we'll try to connect to it and do it.
Hey, I'm Michael Zimmer from UC Berkeley, and I have a twin brother around here somewhere, so don't get too confused. So my research area is in real-time embedded systems, and I focus on systems that have tasks that are timing and safety critical, and these often interact with the physical world through sensors and actuators. So some of these applications can be found in areas such as automotive avionics. And the current approach is to run this software on a real-time operating system on a traditional embedded processor that's optimized for average case performance. The potential problem of doing this is the tasks can often be unpredictable, which means you may have a hard time giving safe and tight bounds on their worst case execution timing behavior. And this is often because the timing behavior can depend on the state of hardware prediction units such as caching and branching, and there's also interrupts that occur, so it's very difficult to figure out exactly how long something's going to take. The other problem is these tasks are often not isolated because when they get scheduled depends on the behavior of some other task, and this means you have to test and verify the entire system. So our approach is, instead of trying to analyze or restrict the programming model, is there a hardware platform that is better for these types of systems? And the solution we came up with we call FlexPRET, which is a 5-stage fine-grained multi-threaded processor that runs the base RB32i. And the basic idea is we have hardware threads that are classified as either hard real-time, and these are going to be scheduled at a constant rate, which means their behavior is independent of any other thread on the system, and it looks like they have a constant logical operating frequency. And then there's also soft real-time threads that just steal unused cycles to try to keep the efficiency of the processor up. So the logical frequency will vary. And then this is an open source implementation. It's done in Chisel, and it's been deployed on FPGA, and we've had it running on Vertex 5, Spartan 6.
My name is Edmund Cote, and unlike many of you here, I'm not an academic. And I found that very early in my graduate work, where I broke one of the rules that Christy was talking about, is don't build your own CPU. So I tried that and failed very miserably. My day-to-day work is as a verification engineer for a large semiconductor company, but I'm here as an individual because I felt very interested by the RISC-V architecture. I learned about it about a month ago, and I decided to put together a project to present to you today. So my observation is that there was not much in the way of testing, random testing, in the RISC-V test suite. So what I have is a proof of concept prototype script tool to generate constrained random instruction streams, and also a method to tie the generated tests to the spike instruction set simulator to get the reference values and generate fully self-checking tests. So if you'll come by to my poster, we can discuss about a low-level constraint programming as it applies to hardware verification. We could talk about how I do the self-checking test generation, and we can chat about functional verification in general.
So my name is Davide Rossi from University of Bologna, and my poster is about parallel processing ultra-low power platform. The main goal of our project is to develop a picojoule per operation milliwatt power enveloped parallel platform for IoT application, and we plan to do this leveraging on tightly coupled cluster of processor, very simple processor operating in near threshold. And also we want to achieve extreme energy efficiency on a wide range of operating point by leveraging on technology-aware architectural design. In the course of this project, we have implemented 2-chip in 28 nanometer FD-SOI technology with both the low power and the high performance flavor of the technology. But also we plan to make the platform scalable, so being able to work in very low power, but also provide high performance depending on the configuration of the platform, implementing multiple clusters and multiple cores platform. We want to make it programmable. It supports several programming models such as OpenMP, OpenCL, and OpenWix, and we make it open, even if at the moment we are implementing everything internally, sharing with partners interested in working together. The objective of my presence here is to develop a platform, a heterogeneous platform, based on a RISC-V processor as a host, with a pulp as a multi-core, many-core accelerator, a large-scale version of this platform with more than 74 cores and 8 clouds.
Hi. I'm also not from academia, but one of the few Bay Area startups that is not doing a messaging app. So we're working on a new processor based along the same lines of RISC-V. We started a bit before the 2.0 ISA spec was released, but it's very similar, and we're hoping to make it closer, even though we have a couple of differences. But our main focus is on high-performance computing, so the top 1% of the top 1% of systems. And we're really trying to solve the big problem eluding the industry, which is reaching exascale, which requires an order of magnitude improvement over the current state-of-the-art of industry, even though, as was published in a paper a bit ago, that the latest Raven 3 does a pretty good job as well. But basically, we're just trying to have a very bare minimum core, with the compute chip being 256 of those cores interconnected with a mesh. Most of all of that is custom. And if you want to talk more, either talk to me or Paul Speckson. Thanks.
I'm also not from academia, nor from this country, like many of you. About 10 years ago, when I was working at Lawrence Livermore Lab, we started an initiative that was called the Open Fabrics Alliance. It implemented, in those days, RDMA over InfiniBand. The HPC community wanted to use InfiniBand for its latency and for many other reasons, but there was no software. So we developed as an alliance with many people involved, the Open Fabrics Alliance, and we have today a worldwide team of about 70 developers that work on this, paid by their companies or by themselves, and we work as a community, open source community worldwide. What does this software have the potential to deliver you with RISC-V? if you look at the bottom here, you'll see something called a hardware-specific driver. If you code that for any interconnect that you want to use, and in this software is taken into kernel.org by Linus himself. So it's in the kernel, and it goes out it's available to every distribution. You can then use your hardware implementation with any of the applications you want that use these APIs, Christy, not ABIs, right? And so you'll see there's IP, there's sockets, there's all the various forms of APIs for parallel processing, SHMEM and all the MPIs and PGAS. There's block storage access, clustered database access, access to file systems. And in addition to this, in the kernel itself, there's a set of protocols that implement standards that are supported by IETF, right? Or what used to be called T10, I forget what that is, but there's SCSI, and there's NFS, and there's Lustre, if you want a clustered file system. Others have implemented a Java machine. Python works with this. AMQP, which is a business protocol for reliable transaction processing over the internet. And NVMe is implemented in this. So if you want to learn more about this, please come talk to me.
Hi, my name's David Hossack. I'm also not an academic. My observation is that, the hardware guys like design processors to run C code basically as fast as possible. And the software guys like to use C because it's close to the machine and they get the highest performance. And this has caused a circular dependence that has kind of locked in a design decision that was made a long time ago that your default integer isn't unbounded. There's a point above and below which bad things can happen. And I'm kind of questioning whether that's a good default. So, my question is, can we add somehow unbounded integers such that small integers are as efficient as the ones that you already have, but big integers still work, you still get the right answer? If you think this is a problem, then please come by my poster. And if you don't think it's a problem, then please read this paper that I cite here. I have a copy at the poster. It reads like a horror story of things that can go wrong. So, yeah, please stop by and tell me how naive I'm being.
So my name is Adam Smith. Until recently, I was a postdoc at the University of Washington, so I've got some academic blood in me, but now I'm trying to be a consultant, and we'll see how that goes. So I'm going to give you a silly introduction to my poster, maybe a more serious one. So if you come to my poster, you'll find about 2 new elementary logic gates, one of which will annihilate the universe. How I've used these to build a probabilistic processor that would be impossible to construct in the real world. But it works in simulation, and that's all I need it to do. How the semantics for it are based on the infinite improbability drive from Hitchhiker's Guide to the Galaxy, and horror stories of how I tried to do this with ARMv6 before, and how I think RISC-V is going to save the day. But more seriously, so I'm working with this thing called probabilistic programming. This is the idea that in order to make machine learning more accessible, people should be able to write probability distributions as programs in familiar programming languages. And then we'll use a bunch of fancy algorithms to answer questions about them, like what is the probability of an execution trace terminating and so on. Lots of people are working on this, but a lot of the languages assume you know a lot of statistics stuff. They assume you don't ever care about having optimizing compilers and debuggers and things that we actually really do like. They sort of fall into 1 or 2 boxes. Either they let you write whatever code you want and then search really, really slowly, or they make you write only with the careful things, the particular things that they've supported. Great search performance, but very limited, restricted language, difficult for the user to work with. So of course I want to combine these things, have the best of both worlds. And in a roundabout way, this involves implementing a new kind of processor. You can think about this as supporting the probabilistic semantics with new instructions at the ABI level. So yeah, we'll just take these new instructions, expose them in C wrappers, and then from any language you want, whether it's C, Python, whatever, you then get probabilistic semantics in those languages, which I think would be a big thing for more people using this stuff. But then how do we actually do this if we can't actually manufacture these things? Well, instead of actually running these things in parallel universes, as soon as you try to do one of the fancy things, we slurp up the memory image, hand it off to a SAT solver, find a solution, then replay it where you can debug it and so on. This is sort of like probabilistic model checking, but swept under the carpet of an instruction set. I tried to do this once before with ARMv6. It worked enough to make my funders happy for a while. We were generating math textbook problems. They were confused as to why I was designing a processor for them. And I have a Python library that lets people play with these ideas even without all the search implemented. But in the future, I'm going to be hopefully switching to RISC-V using a real hardware description language instead of my own this time. Actually, applied logic minimization to make the circuit smaller. The general trend will be, after I gather up all your wisdom here, if you come to my poster, I'll start thinking more like a processor designer and not an AI programming language stats person. Come to my poster.
So hi there, my name is Yu Hao. I'm a PhD student from UT Austin, and you can find more information about me in that link. And there's a picture of me in case you want to talk to me, but note that my hair has been much shorter now. Right, so our observations that architecture innovations are typically driven by upheavals in the software programming models or application characteristics, right? So, I mean, a great example is GPUs, which came out and became mainstream because of, the emerging data level parallel applications. And our argument is that we are actually seeing another sort of software program model evolution or shift, and that is the event-driven application or event-driven programming model. So, actually, event-driven applications are everywhere, right? If you think about from sensor-rich IoT applications to mobile devices to even cloud services such as Node.js applications, which by the way is what we are primarily looking at right now. Event-driven program model or execution model is there, right? So, and our argument is that existing general-purpose CPUs are actually ill-suited for these event-driven applications, and the reason are twofold. So, first of all, event-driven applications are typically, they have typically very poor instruction locality. And the reason is because you have various types of events, they are interleaved with each other. And this interleaved execution actually pollutes the locality. And CPUs are actually designed with locality in mind, right? So obviously there's a mismatch here. And the second reason is that, typically event-driven applications, they employ, a single monolithic queue, which means it loses parallelism. Even though all, some events in the queue, they can be executed out of order or concurrently. So, what we are really trying to do is to come up with a new architecture that's, that best supports the event-driven applications, and that's what we call the event-driven architecture, or EVE. And here's a proposed or our, imaginary architecture that we have on our minds right now. So basically, we have an event fabric, which is a sea of event cores, and each event core is specifically dedicated to one instance of event. And each event core has its own cache structure and branch prediction so that the locality can be preserved. And at the same time, because as you can see, there are multiple instances of the event cores, we can extract the parallelism that's inherently there in these applications. Our philosophy of each event core is that we want this to be general purpose, and at the same time, we want this to be extensible so that we can add some sort of architectural specialization, and that's why we're very interested in RISC-V cores. And you can even imagine that the event fabric can be partitioned to a set of customized logics that are specialized for those super hot events, and the customized an array of RISC-V cores that are for those not so hot events. I guess that's pretty much what I have. So I'm keen to listen to you guys' inputs.
Hi, I'm Sagar Karandikar. I'm an undergraduate in the Aspire lab, working alongside the group of students you see on the right. And our poster is about hardware acceleration of key value stores. So we found that in many data center applications, in our case Memcache in particular, about 86% of total request latency is spent on the CPU actually doing some processing. So our goal was to be able to actually serve popular key value store GET requests without involving the CPU at all. So in order to do so, we created a software managed cache attached to the ROC CPU interface to Rocket, and also attached directly to the network interface card, so it can respond to queries without involving a CPU. So to benchmark our system, we actually pushed it onto an FPGA. So we had RISC-V Rocket running at 50 megahertz. And to that, we attached a network interface card built from some Xilinx IP and a 1 gigabit SFP. So this was actually the first RISC-V system that you can sit down and SSH into. And to that, we attached our hardware key value store accelerator. along with a traffic manager, essentially a piece of hardware that looks at incoming packets, determines if they're memcache UDP packets, and forwards them to the accelerator as necessary, along with a DMA engine. And of course, this is all written in Chisel. So a brief overview of our system design. So we have memcached running on Rocket. We have requests coming in from the network. They get fed into the traffic manager. It'll check to see if they're memcache UDP packets. If so, they get sent to the accelerator, which checks its local cache. If it has the value for some key, it'll construct the response and respond directly without involving the CPU at all. Otherwise, it'll pass the request to the DMA engine for software processing on Rocket. So we had two primary benchmarks as part of our evaluation. First, we just did a raw performance test. So here we found that we could actually beat software memcache by a factor of 10. So seeing a response to a GET request in software took about 1,700 microseconds, and our accelerator was able to respond in just 150 microseconds. The replacement policy of our system is software tunable, using a rather basic basic replacement policy that just looks at kind of the last short period of time and looks at what's popular over that period of time. We were actually able to handle about 40% of requests at our 10x latency reduction on a realistic benchmark based on some internal Facebook traces. So if you're interested in learning more about our project and checking out our live demo, come see our poster.
Thank you, and thanks. Let's thank all the speakers for being on time.